ครับสวัสดีครับทุกท่านครับก็ขอต้อนรับทุกท่านนะครับเข้าสู่การบรรยายพิเศษนะครับวันนี้หัวข้อเรื่องเจาะลึกการสำรวจอวกาศขององค์การสำรวจอวกาศญี่ปุ่นหรือว่า JAXA นะครับวันนี้ทุกท่านก็มีความตั้งใจที่จะมาลงทะเบียนฟังเรื่องราวที่น่าสนใจในวันนี้นะครับก็ขอต้อนรับทุกท่านเข้าสู่ห้องบุษกรนะครับของอาคารเนคเทคสวทชนะครับที่อุทยานวิทยาศาสตร์ประเทศไทยแห่งนี้นะครับผมปริทัศน์เทียนทองนะครับเป็นผู้ประสานงานของโครงการความร่วมมือระหว่างสวทชกับ JAXA นะครับรับหน้าที่เป็นพิธีกรในวันนี้นะครับ Good afternoon, ladies and gentlemen. Welcome to this special lecture, a deep dive into JAXA space exploration missions, which is being held here at Bussakorn room on the first floor of the NECTEC building within the NASA at Thailand Science Park. I am Paritat Thien Thong, the coordinator of collaboration project between NASA and JAXA, and it's my honor to serve as your master of ceremonies today's event.วันนี้นะครับถือโอกาสพิเศษที่เราจะได้ร่วมเดินทางไปสำรวจอวกาศร่วมกันนะครับผ่านมุมมองและประสบการณ์ขององค์การสำรวจอวกาศญี่ปุ่นนะครับหน่วยงานชั้นนำด้านอวกาศของโลกนะครับแล้วก็นะครับเพื่อเป็นการเริ่มต้นกิจกรรมในวันนี้นะครับก็ขอเรียนเชิญนะครับดร.จุฬารัตน์ตันประเสริฐนะครับรองผู้อำนวยการสวทช.ให้เกียรติขึ้นกล่าวต้อนรับทุกท่านอย่างเป็นทางการครับขอเรียนเชิญครับ
Dear distinguished guest speaker, Dr. Masaki Fujimoto, Director General of the Institute of Space and Astronautical Science (ISAS) and Vice President of the Japan Aerospace Exploration Agency or JAXA. Also, dear Ms. Maki Yoshihara, the Manager for the Director of Management and Integration Department of ISAS. Also, Mr. Takumi Inoue, the Advisor to the Director of Management and Integration Department ISAS. And lastly, but not the last, Mr. Takehiro Nakamura, Director of JAXA Bangkok Office. Nice to meet you all again. On behalf of NASDA, or the National Science and Technology Development Agency, it is my great honor and pleasure to welcome all of you to today's special lecture on the topic of a deep dive into JAXA space exploration missions. เรียนท่านแขกผู้มีเกียรติทุกท่านในนามของสวทช.ดิฉันรู้สึกเป็นเกียรติและยินดีเป็นอย่างยิ่งที่ได้ให้การต้อนรับทุกท่านในวันนี้เข้าสู่การบรรยายพิเศษในหัวข้อเจาะลึกโครงการสำรวจอวกาศของโครงการสำรวจอวกาศญี่ปุ่นเรื่องราวของอวกาศไม่ใช่เรื่องไกลตัวอีกต่อไปแล้วนะคะแต่เป็นโอกาสที่จะให้องค์ความรู้ใหม่ๆกับพวกเรานะคะสวทช.เราเองเนี่ยให้ความสำคัญกับการสร้างแรงบันดาลใจแล้วก็การอัปเดตความรู้ด้านวิทยาศาสตร์และเทคโนโลยีใหม่ๆอยู่เสมอนะคะวันนี้จึงเป็นโอกาสที่ดีที่เราจะได้รับฟังเรื่องราวที่ exclusive นะคะจากผู้ที่เป็นหัวใจสำคัญของภารกิจอวกาศระดับโลกนะคะวันนี้เราโชคดีและเป็นเกียรติมากๆค่ะที่จะได้ดร. ฟูจิโมโตะ มาซากินะคะมาแบ่งปันเรื่องราวที่น่าตื่นเต้นให้เราฟังกัน2ส่วนหลักๆนะคะส่วนแรกจะเป็นเรื่องของข้อมูลเบื้องหลังความสำเร็จของโครงการฮายาบุสะ2นะคะเป็นภารกิจสุดยอดในการเก็บตัวอย่างจากดาวเคราะห์น้อยริวกูกลับมายังโลกได้สำเร็จนะคะจะมีคนไทยเราจะได้ชมตัวอย่างจากดาวเคราะห์น้อยริวกูด้วยนะคะในงาน All Warfare 2025นะคะซึ่งจะจัดพรุ่งนี้แล้วนะคะจะเปิดงานพรุ่งนี้เป็นวันแรกวันที่9ถึงวันที่17สิงหาคมที่ศูนย์สิริกิติ์นะคะโปรเฟสเซอร์ก็จะไปอยู่ที่งานด้วยนะคะทราบว่าพรุ่งนี้ไปแน่แต่วันอื่นไม่แน่ใจเดี๋ยวอาจจะลองถามท่านดูนะคะสวทช.เราเองก็ไปจัดนะคะอยู่ในโซนดีเราจะนำนิทรรศการแล้วก็กิจกรรมแล้วก็ IP ต่างๆที่สวทช.มีนะคะไปนำเสนอให้ได้รับชมแล้วก็ให้ผู้ประกอบการได้พิจารณาในการถ่ายทอดเทคโนโลยีร่วมกันนะคะอีกโครงการหนึ่งนะคะดร. ฟูจิโมโตะจะเล่าถึงภารกิจแห่งอนาคตค่ะเรื่องของยานสำรวจดวงจันทร์ของดาวอังคารนะคะหรือ MMX เข้าใจว่าจะมีตัวอย่าง อยู่ในรูปนะคะจะมาเล่าให้ฟังค่ะที่จะไปไขความลับของดวงจันทร์โฟบอสรวมถึงเรื่องราวที่สำคัญมากๆอย่างโครงการป้องกันดาวเคราะห์น้อยพุ่งชนโลกนะคะที่ญี่ปุ่นมีบทบาทสำคัญอยู่ด้วยก็เชื่อว่าวันนี้ทุกท่านนะคะที่ได้มาร่วมอยู่ในวันนี้ด้วยกันจะได้ทั้งความรู้แรงบันดาลใจแล้วก็มีไอเดียใหม่ๆกลับไปอย่างแน่นอนนะคะ and now it is my great privilege to invite Dr. Masaki Fujimoto to the stage to deliver his lecture thank you very much
ครับแล้วก็วันนี้ขอเรียนเชิญดร.จุฬารัตน์นะครับมอบของที่ระลึกให้กับท่านวิทยากรครับดร. Fujimoto นะครับ At this time I would like to invite Dr. จุฬารัตน์ to present a token of appreciation to our distinguished speaker Dr. Masaki Fujimoto JAXA Vice President and ISAS Director Generalครับ โอเคเดี๋ยวผมเก็บไว้ก่อนครับครับ And now I would like to invite Dr. Churalat to present a token of appreciation to JAXA and ISAS member. First, Ms. Masaki Yashihara, Manager of the Director of Management and Integration Department, ISAS. And Mr. Takumi Inoi, Advisor to the Director of Management and Integration Department, ISAS. And Mr. Takehiro Nakamura, Director, JAXA Bangkok Office.ขอบคุณดร.จุฬารัตน์เป็นอย่างสูงครับ And now please give a warm welcome to Dr. Fujimoto. Thank you.
I had to push it for a long time. So, thank you for coming to this talk. My name is Masaki Fujimoto. I'm the Director General of the Science Institute of the Japanese Space Agency. So, what is space science? We want to explore space. So, in order to understand better about space, sometimes it's important that we get beyond the atmosphere and make some observations. Or we should visit the solar system bodies and explore deeper. So in today's talk, I would like to describe the latter part, the solar system exploration of what we have been doing in the past 10 years or something. I think this slide really highlights our activity in the past 5 years. On the left-hand side, what you're seeing is the sample return capsule that just landed in Australia, Umira in Australia. So this is like the grand finale of the Hayabusa 2 mission. And on the right-hand side, what you're seeing is the slim spacecraft that managed to land on the surface of the moon. So we did make a nice big success, and then what we will do from now on. That's the topic of today. So Hayabusa 2, the asteroid sample return mission, and then the lunar lander, SLIM. These are very eloquent in telling us how we do our solar system exploration. And we think with this success, I think we are ready to talk about Mars landing program. Mars landing is what everybody wants to do. But on the other hand, US NASA has done a lot already. So what do you do? And I think we have the idea now, based on this nice success in the past. So those are the topics I'll be dealing with, and the reason why I'm here, especially in Bangkok, is because of this nice event. And I really like the fact that people appreciate this exhibition. As you can tell from how the Ryugu sample Ryugu particle look like, it's just it looks like a regular sand particle, nothing else, nothing special. But what you really should appreciate is that from this regular-looking sand particle, you can learn about early days of the solar system, about the processes that made Earth to be a bioplanet, a habitable planet. And I think by looking at this sample in the exhibition, I think you get to think about this. The sample itself is nothing sexy, but it makes you think, what kind of technology we have that we can learn about the early days of the solar system by just analyzing that small particle. But anyways, let me move on to describe what the Hayabusa 2 mission was like. So Hayabusa 2 is a sample return from a primordial asteroid. And what I mean by primordial asteroid is like this. So this is what the solar system looked like when our sun was born. So in the central part of the panel, you see the proto-sun. So sun is about to be formed. And what you're seeing around the sun is the protosolar disk. And you can tell there's a demarcation line here. So inside this line, the temperature of the disk is hot enough that water is in the form of vapor. But if you go to the outer part of the solar system, the temperature goes down. So water, H2O, in this outer part of the solar system is in the form of ice, solid particles. And what happens in this protosolar disk is that the disk is composed of dust particles. Dust particles come together and eventually form planetary bodies like Earth or Mars or whatever. So what happens is that solid particles come together to form planetary bodies in this protosolar disk. And the question is, as the planetary bodies form, what happens to the water, H2O? Inside this line, which we call snow line, inside the snow line, temperature is high, so the water is in the form of vapor. So whatever dust particles do, vapor doesn't care. They just stay as vapor. But if you are outside the snow line, H2O is in the form of ice particles. So when the dust particles come together, they behave the same. So what does that mean? Planetary bodies born outside the snow line, they can contain water, because when you're forming a planetary bodies outside the snow line, you're collecting ice particles together. So planetary bodies born outside the snow line, they contain water. But if you have formed inside the snow line, you're born dry. So now the question is, where was Earth formed? Do you know where? Actually, Earth was formed inside the snow line. That's what the theory tells. So which means is that Earth was born dry. And if Earth stayed dry ever since then, we wouldn't be here. Earth would not become a life-bearing planet unless somebody brought water to proto-Earth that was dry. So what we think is that it must be the small bodies born outside the snow line that was hitting proto-Earth, that brought water and organic materials, all those preconditioning that's necessary to make our planet life-bearing planet. So we think somebody like Ryugu, the target asteroid of Hayabusa 2, was hitting Earth, was precipitating to proto-Earth and brought water to make our planet habitable at all. So that's the reason why we are going to Ryugu, the primordial asteroid, and a small body that was born outside the snow line. So we're going to get there and get the samples back from Ryugu. But how do we do this? So this is how we do this. Now, what you're seeing is the surface of Ryugu, and then have the two spacecraft. So it's going to touch down on the surface like this. And when we make this touchdown, it's only the tip of the sampler horn that should touch the surface. And when you make that touch, when you touch the surface, we shoot the bullet, and then the fragments of the surface will come into the spacecraft, and we bring that fragments back to Earth. So because of that design of the operation, one thing we have to worry about is the surface roughness. The length of this sampler horn, well, this is the tip of the sampler horn, and this is the main spacecraft body. And the length of the sampler horn is 1 meter. And during the operation, or during the touchdown operation, it's only the tip of the sampler horn, but no other part of the spacecraft that should touched by the asteroid. So the length of this sampler horn is like 1 meter. And if you include a safety factor, we expect a large area without rocks that's not larger than 50 centimeters to be there on the surface of the Ryugu, of the asteroid Ryugu. So we were thinking that there will be a large enough area that doesn't have rocks larger than 50 centimeters, and then we can land there and get the samples. But when we arrived at asteroid Ryugu, this is what we found. It's rough everywhere. There's no large area which doesn't have rocks larger than 50 centimeters. It seems that larger rocks is everywhere. Then where will we land? So the issue here is that we had the plan, but we made that plan without knowing the details. The size of this asteroid is 1 kilometer from there to here. So when you make a ground-based observations, all we had known is that it is a primordial asteroid. That's what we had known. It must be a small body that was born in the outer part of the solar system. We had known about this, but we didn't know these details. That's necessary to do the detailed planning of the operation. But that's what we have to do anyway. We had no ways of knowing these details, so we have to launch a spacecraft, and then when we arrived at the destination, we realized that we have a problem. So it's a very unfriendly surface condition, that which is known only after arrival to the target asteroid. And what do? It's a sample return mission. We have to do something. So there was a necessity to develop a new technique only after arrival to the target asteroid. And that new technique is for pinpoint landing to a small spot on the surface of the asteroid. So this is what the team did. They have developed a new tool. They have developed a new operation scheme utilizing something by the name target marker. So target marker is something that shines very bright on the surface of the asteroid once you set it. So it's like an artificial landmark that you can set on the surface of the asteroid. And once you set that landmark, you can navigate your spacecraft more precisely, much more precisely. So this is the critical operation. Now, the spacecraft is at the altitude of 12 meters after dropping the target marker on the surface of Ryugu, the asteroid. So what you are seeing here is the target marker. And this is a movie, and what I will show you is a demonstration that we have the technology to precisely navigate the spacecraft. What I will tell you is that now we have the landmark on the surface. And by referring to this space, to this landmark, we try to control the spacecraft autonomously, by the way. It's all autonomously by the spacecraft. So what the spacecraft will do is to stare at this point and try to correct its position so that this bright landmark will stay in the middle of the camera, field of view of camera, while spacecraft increases its altitude. So here's the results. So our altitude is going up. Now it's 30 meter, 40 meter. And as you can see, the landmark stays in the middle of the camera, which is good. So this movie is like a demonstration that we have this tool, this landmark on the surface, and then this navigation technology, or autonomous algorithm, that we can precisely control the position of the spacecraft, and we are ready to land on a small spot on the surface, small flat spot on the surface. But we do have a problem because back then we're still like amateur racing driver. So we had a plan to land in that red circle, but we didn't drop the target marker inside of it, but target marker was dropped here. And then the team looked around and realized that there's a small flat area, but something that's closer to the target marker, the landmark. Now the question is, do you go for the red circle or do you go for the green circle? The bigger one, but that's remote from the target marker, or the smaller one that's much more closer. And the engineers went through the trade-off study, and then they come to the conclusion that this green circle is easier to land. But how small is this spot? Here's the size of the spacecraft. So you can tell that the size of the spot that we are trying to land is almost exactly the same as the size of the spacecraft. So it's like a hole-in-one, going for the hole-in-one situation if you play golf. So this is the day, February 22nd, and now this white bright spot is the target marker. This is the landmark. And now the spacecraft is at the altitude of 12 meters, I think, or 14 meters. It's waiting above the surface of the asteroid, making sure that it's in the right position. And then, here we go. Oops. No, I should, yeah, okay, it's going, moving. All right, so it's judging whether it's in the right position. And now it did, so now it has convinced itself it's in the right position. It has started to make the free fall to the surface. And then the tip of the sample horn touched the surface without any other parts being hit by the rocks. So it was a very nice thing. And then, so we made a nice touchdown, and everything went smoothly. So there's no way of confirming how much samples we got through this operation, but everything went smoothly, so it must be okay. That's what we thought. But then we didn't stop here. We didn't stop here, but instead we moved on to perform this kind of impact experiment. Okay, so what we are doing here is that we deploy a device by the name impactor, and then this impact will reform itself into something like a bullet, and then shoot the surface. So this is an impact experiment to create an artificial crater on the surface of the asteroid. The reason for doing this is that crater gives us a lot of information in planetary science, and but on the other hand, we don't know much about the crater formation process. we know only, we know about the crater formation process from our knowledge on the surface of the moon or Earth, only under the strong gravity condition. But we know nothing about crater formation process under small gravity, which this asteroid provides. So if we perform this experiment, we should be able to learn about the crater formation process under the microgravity. But in doing so, there will be much debris coming out of the experiment. So after deploying the impactor, the two spacecraft, main spacecraft, should evacuate into a safe position. But in doing so, but if you do so, you're not going to observe the experiment itself. So at the same as like we did deploy the impactor, we also deployed a small camera, so that this small camera can witness the experiment and give us the data back. So it's a poor man's complicated experiment. You have two deployments, and each of them are very small. You have to do it precisely, and it's not easy, and it's cheap. But we managed to do this very successfully. So what you're witnessing here is the humanity's first footage of the crater formation process under microgravity. So now the impact has touched the surface. So what you're seeing is a debris curtain forming and expanding in time. And we're learning a lot from this footage. So it was an impact experiment. It was to study the crater formation mechanism under microgravity. And we got the footage, so it was very successful. But at the same time, impact experiment means that we have excavated unweathered surface materials. And they are ready for sampling. They're sitting on the surface, so they are ready to get sampled. So what I mean by this is that from the first touchdown, we got samples from the surface, and they're exposed to space environment. So they're space weathered. And we don't think that's not too bad, but it would be nice to get some samples from the subsurface, which is unweathered, and we can compare the two and make sure that even the first samples are good enough. So that was the point. And then we have succeeded in the impact experiment. So why don't we try to get the excavated subsurface materials and get the samples? Indeed, we had that idea already when we performed the impact experiment. So crater was created there, and it was created close to a very flat area of 10 meter size. So the idea here is that if you make a crater here, excavated subsurface materials could be sitting on this flat area from where we can get the samples. So that was the idea. And then we did make a crater. So then why don't we drop a target marker inside this area so that we can get ready to do the sampling. The team thought about it. It was a super successful impact experiment. Let's move on, go for the second touchdown. And then they went on to drop a target marker into that flat area, but then realized something wrong happened. And then they stopped the operation, but they understood what's happening. And they talked to the leadership that they should continue. They want to continue. They want to go for the second touchdown again. But of course, as you can understand, there was an elevation in the pressure to stay safe and don't go for the second touchdown again. And the team was under much bigger pressure. They have to do everything correctly, of course. But at the same time, what's really funny is that maybe it's not that spot I have identified, but there's a better spot to get the samples from. So the leadership was saying that, don't do this. But the team members, the younger team members, thought that, oh, there's a better way of doing this. So it was a kind of funny situation. But then the team was under big pressure anyway, so they have to complete everything perfectly. And there's no chance of taking the risk of losing the spacecraft, of course. But the young team members really did a great job. So they have identify a new spot where you can get the nice samples from. And what you can tell from this slide is that this is where the artificial crater was formed. And the original spot that we were thinking was somewhere around here. And that light blue thing is the new spot. And you can tell that the surface is darker on the upper side of the panel. But we think it's darker because they are covered with subsurface materials. So better than the spot we had been thinking here, the new spot, it's safer and it seems to be covered with subsurface material better. Then why don't we go for that spot? And the team moved on to drop the target marker, this time very nicely within that landing ellipse. And so even though there was a big discussion not to go for the second touchdown, the team did a great job of performing the second touchdown very, very nicely. So we performed 2 touchdowns on the surface, the first touchdown and the second touchdown. Second touchdown very likely acquiring subsurface materials excavated by the impact experiment that took place between the 2 touchdowns. And we left Ryugu in November 2019 when none of us knew the word COVID-19. So November 2019, leaving the Ryugu, and it is supposed to arrive at Earth in December 2020 in the middle of the pandemic. But under the pandemic, we have to do this anyway. So with the help of lots of people, especially from Australia, we did the recovery of sample return capsule in the desert of Umira. So what happens on this day is that the Hayabusa 2 spacecraft come back from Ryugu and come very close to Earth, and then it super precisely pitches the sample return capsule into the desert of Umira in Australia. And in the next movie, you will be seeing the fireball created by the sample return capsule. Now you are standing in the city of Kubaperi, 400 kilometers north of Umira, where the sample landed, and you're going to see the fireball created by the capsule. Here we go. So a capsule coming from northwest and now going down towards south-northeast. This movie was created by synthesizing many photos taken, synthesizing real photos taken in the city of Kubaperi. And this, viewing angle is exactly the same as if you're standing there and looking up in the sky. So this fireball is created at the altitude of 40 kilometers. And so for us who was in Umira for the capsule recovery operation, this fireball is only the alarm saying that this is not a drill. So after this, coming down towards altitude of 10 kilometers, the capsule has to deploy a parachute, and it has to start the beacon signal. Without the parachute, it will be a crash on the surface, and without the beacon signal, we don't know where the capsule is, so we cannot recover it. So it wasn't, this moment was like the beginning, and for us, the most critical time was like when the capsule is at the altitude of 10 kilometers, which is supposed to happen a few minutes after this. So our heart was beating like crazy between this time and then, and until we got the radio signal saying that the beacon signal was received. So, but it went on well, and finally the capsule landed safely onto the soil of Umira. This is the sample return capsule, and this is the parachute. So we went there quickly. Of course, we knew where it landed, so we went there quickly with a helicopter and picked it up. And we send it back quickly to Japan so that we don't get the terrestrial contamination of the samples. And in a special facility in Japan, back in Japan, we opened up the capsule to find that it was a big catch. So these are the Ryugu samples, which you will be seeing tomorrow in the exhibition. Yeah, these are the samples coming back from Ryugu. And because we don't want to contaminate this, and because there are so many scientists all over the world who's willing to study these samples, we do have a special facility like this where we handle the samples. Oops. So what we're doing here is that we pick up each particles like this, and then separate them into different cases so that they will be ready to be shipped to the scientist who wants to study this. That's what we are doing now. Okay, so then, yeah, HABSA 2. If you're going to the exhibition tomorrow, starting tomorrow, there's something you might want to keep in your mind so that you can enjoy your experience better. I think there are 5 key issues. So why do we go to Ryugu? Or why asteroid sample return? Well, JAXA, Japanese Space Agency, is much smaller compared to NASA. But in space science, you have to do something really, really interesting. Otherwise, nobody cares. So what's the best thing to do if you're not as large as NASA? What in planetary science can you do? I think we thought it must be the asteroid sample return. It's not an easy mission, of course, and there was a long and winding road towards the first touchdown. As I said, you have to invent a new way of navigating the spacecraft precisely to the small spot on the surface, which the team did. And there was then we dared to perform the impact experiment. You might have been thinking that we barely managed to perform the first touchdown. Then why do you try to do more? You went through all the long and winding road to get the samples, and why don't you just stop there and do nothing more? You could have thought about this. But we went on to do the impact experiment because, again, we have to be bold. Otherwise, we're nothing. We are much smaller than NASA, and if we don't go bold, we're nothing. That's the thing. And that applies to the second touchdown as well. Yeah, the second touchdown itself as well. We did perform the second touchdown because if we don't even try to do the second one, we're nobody. And sample return capsule recovery was performed under pandemic because we're determined to do so. So there are so many things to bear in our mind, and that really made us identify our character in the global exploration landscape. So in parallel to this HABSA 2 mission, we were preparing the lunar lander. SLIM is the name. It's the smallest lander on the moon, and it's for technology demonstration of pinpoint landing technology. By pinpoint landing, what I mean is that you want to land to the spot where you really want to land. So it's a small mission, the smallest lander on the surface of the moon, but I think it's a smart mission. And the reason why I care about the combination of small and smart is because of nowadays everybody is talking about going to the moon and then on to Mars, including Thailand, of course. You are a member of this Artemis Accord. And in this context, we talk a lot about this human explorations, sending human to the surface and then bringing this big asset to the surface. That's nice. Of course, that's nice. But in addition to those big things, in Artemis, we're talking about let's go to Moon and Mars together, including the commercial partners. And then in that context, it's much better to have small and smart thing because that's more cost effective. That's the initial hurdle is much lower if you manage to create a platform for small and smart mission. So that's what we thought. Maybe we should prepare a small and smart platform so that's going to be the way that's going to be the platform for more and more people to join this Moon and Mars exploration. So that was the idea. So the SLIM was launched in September 23 and got into the orbit around the Moon in December of the same year. And then in January next year, about a month later, we were ready to do the landing operation, which starts from this reverse thrustering to lower the orbit. And so what happens is that you start the reverse thrust at the altitude of 15 kilometers and come down to the altitude of 7 kilometers. And during this powered descent phase, we perform 3 times what we call image-based navigation. So that's the new technology. Conventional technology is based on the radio communication. But now, SLIM has a map in its mind, and it takes the pictures of the lunar surface right beneath it. And by comparing the two images, you can tell where you are compared to where you want to be, and you can correct your position. And at the altitude of 7 kilometers, the error bar, the error between where you wanted to be and where you actually were, was only 100 meters. If you use the conventional technology, the error will be like 10 kilometers. So it's like a 3 orders of magnitude improvement just by performing this image-based navigation. From 7 kilometers down to 50 meters, where it was hovering for a while, we have performed this optical image-based navigation 10 times, and as a result, at the altitude of 50 meters, the precision, I mean, the error between where you wanted to be and where you are was only 3 meters. So again, this is really like a 3 orders of magnitude improvement. And I would like to remind you that this very nice technology demonstration was performed by the smallest lander ever. So it's a small and smart way. You know, you land where you want to go. You just do the job you want to perform, and that's it. So I think that should be the way of inviting many people to join the lunar exploration. So we think the pinpoint landing technology was established, and there was only 50 meters left. It was only 40 seconds left in terms of operation time, but something wrong happened. The thrust from main engine all of a sudden became almost half of what it used to be, and the reason is obvious in the next image. One of the nozzles is now on the surface of the moon. So, yeah, this happened. It was only 40 seconds left, but this happened. But the SLIM is a smart spacecraft. It has noticed that something is wrong, so it shifted to the contingency mode by itself. Yeah, losing one of the 2 main engines at it was only 40 seconds, but still. So the SLIM is a smart mission. So this was the original plan, and it realized that something wrong happened. So it autonomously shifted to the contingency plan, and so leaving some of the options are not available anymore. But it did manage to make a soft landing. So it was a soft landing, and that's why we got all the data back, and that's why I could show nice pictures as well. So it was a soft landing, but of course, because losing one of the main engines, it ended up in abnormal orientation after landing. So how wrong was the orientation? It was this wrong. It was almost looked like an upside down orientation. But I think you must be thinking, so who took the picture, right? It's not the orientation. It's less the orientation, but more who took the picture. And if you remember this slide, even though we are in the contingency mode, we kept the option of releasing the 2 small robots. You normally you don't do this, right? You're in the contingency. Why do you don't do anything else but to make the main spacecraft survive? That's what you would think. But somehow team maintained this option of releasing 2 small robots, which did the job. So it was this small robot, it's one of them. We call it SORA-Q, 200-gram mass, baseball size, very small, like this size. And it was in collaboration with Takara Tomy, the toy company, and then Sony. Of course, you know what Sony is. And yeah, it's really a cute robot, baseball size, and very nice design because it's coming from Takara Tomy, of course. We wouldn't be able to make such a nice design. So what happened is that Slim, even though it was in a contingency mode, still it released 2 small robots on the surface, and after landing, it's this smaller one which took the picture of the Slim spacecraft and sent the data to the other robots, small robot, which is only 2 kilogram-ish, and then it's the other robot which sent the data back to Earth. So what does it mean? Slim is the smallest lander on the surface of the moon. And it has demonstrated the pinpoint landing technology. But in addition to this, it has also demonstrated that these small assets like this, they can do some nice work. And the reason we decided to make a pinpoint landing to this spot here is that from this crater, it seems that when this crater was formed, there are lots of rocks from the deep interior of the moon that get scattered around it. So why don't we land next to one of those rocks that's coming from the deep interior and study it in detail instead of diving deeper into the moon? That's the plan. So even though we had a problem, Slim was reactivated about a week later and performed the spectroscopic observation of those rocks coming from the deep interior. So it did the job, which is good. And it not only did the job, but it survived the lunar night, which is very, very tough. So that's a bonus result anyway. So what I really want to tell you is that Slim not only demonstrated the pinpoint landing technology, but he also showed that small robots can do a nice job in in Mars and in Moon and Mars exploration. Yeah. So key issue is that yeah, it's a small mission, and small robots, but they're smart. So we did the lunar landing, the moon done. Then are we going to Mars next? Good question. But it's not that simple. But on the other hand, it's good to think about is Mars next, because Mars is so attractive, and I think we have to think about this. But on the other hand, NASA has done a lot. So how dare we, who's much smaller than NASA, dare to think about it? This is what NASA did. NASA is doing now. Big rover with the nuclear power source, and the size of this, the mass of this rover is like 1,000 kilogram, and it's attached with this nice drone system. So this big one could move only slowly, but you have another flying module that can make the reconnaissance around the big body. So big rover. So it's really nice what they're doing, and something unreachable for us. Then what do you do? And we have done something nice with the Slim mission, the lunar lander. So what does it mean? That can that accelerate our thinking about our Mars landing program? And I think it does. Well, first, we don't go directly to Mars itself, but we go to Phobos, one of the Martian moons, a small body that's flying around Mars. So not Mars itself, but one of the Martian moons, Phobos. And well, science-wise, it's really interesting because as I said, we're really interested in connection between the outer part of the solar system and the inner part of the solar system during the early days of the solar system. And if you look at this, Mars is really sitting at the gateway position. And Phobos is a small body rotating around Mars whose origin is unknown. So if you go to Phobos and get the samples and start to learn about the origin of Phobos, we should be able to learn about the processes connecting the outer part and the inner part of the solar system. That's planetary science. And also, from the space engineering point of view, there's so many things you can do with this Phobos sample return mission. So it's an MNX itself, Phobos sample return mission, to be launched next year, 26. I think it's going to be a very nice mission, and everybody, and many people like NASA or your European colleagues, they are part of the mission, and they're really looking forward to the samples we will be returning from Phobos. So it's a nice mission, but meanwhile, I've been thinking that if we can identify one more key item that would feature our way of doing Mars landing, we can go ahead. And what can that be? I didn't want to give up because Mars landing is so attractive. Of course, on the other hand, it's not easy unless you have the strong reason. Unless you have the strong drive to tell, hey, this is our way of doing it, so we should do this. So I've been thinking about this, and I think I have it now. It's a technology by the name inflatable soft aeroshell. It looks something like this. It's an inflatable thing, as you can tell, as you can see. So what I mean by this is that in order to do the Mars landing mission, you have to make the entry, descent, and landing throughout the Martian tenuous atmosphere. And in the NASA's way, because they are interested in bringing 1,000-kilogram rover to the surface, they have to go through a very complicated process of having a big heat shield and deploying a supersonic parachute, and then the thruster at the last stage of the landing. It's complicated. I don't think we can do this by ourselves. But with this inflatable aeroshell technology, as long as you're interested in a lightweight mission, not like the one that NASA is interested in, but our way of doing things, if the mass is not too high, this one alone is enough. You don't need a heat shield, you don't need a supersonic parachute, especially the supersonic parachute is really a tricky beast. But you don't have to worry about this. All you have to do is inflate this all the way up in high altitude and then drop your lightweight thing to the surface. We came up with this idea. We came up with this idea because we're interested in small and smart missions. And besides, we only have a limited launch capability, limited budget, and we're interested in doing things more frequently. So I think we have a nice way ahead. Yes, we're interested in lightweight access to the Martian surface and do it frequently with our partners. So it's the JAXA's way of doing Mars landing mission, lightweight access to the Martian surface. And it's not only affordable, I think it will democratize Mars landing exploration. Mars landing exploration is everybody's interested in. So why don't we provide a nice platform that will lower the initial hurdle so that many newcomers can join and have fun exploring Martian surface. So this is what we will do. Eventually there will be a 200-kilogram-ish rover to be delivered to the surface by this technology. And we will do this in a smart way. The transportation vehicle will be a common one. We will keep on using the same thing as far as the transportation vehicle is concerned. But at the same time, we will make a step up 3 times. And in early 2040s, I think there will be a rover of 200 kilogram size-ish on the surface of Mars. But we don't do it, we don't jump to this. The first one step will be very decent. The goal for the first step will to demonstrate, to do the tech demo of the JAXA's way of approach to the surface. So having a small lander, three small lander is enough to reach the goal. But because there will be a spare capability of the transfer vehicle at the same time, I think multiple small assets will be the customer to this transportation service. So it's really like Mars landing exploration for all. So so what we have in our mind is that distributed system of multiple small assets, each performing a very focused job, but as a whole, we do something really nice, and it can work as a welcome package for those newcomers who's interested in Mars landing exploration, who will never have a chance to join big missions like by NASA. So here's a summary slide. We've been doing things differently, but in a meaningful way. And the success of Hayabusa 2 and SLIM really made us convinced that there's a role we can play in the global exploration landscape. So nice mission, Hayabusa 2, SLIM, and we're moving forward with MMX, and maybe by the same style, we can move on to do the Mars exploration, Mars landing exploration, which is really like a holy grail in space science. So that's all I have to say. Thank you very much.
Thank you very much, Dr. Fujimoto, for that truly enlightening and inspiring presentation today. วันนี้นะครับผมเชื่อว่าหลายๆท่านน่าจะมีคำถามนะครับที่อยากจะเรียนถามวิทยากรของเรานะครับมีเรื่องต่างๆมากมายในการสำรวจอวกาศที่ทุกคนอาจจะอยากรู้อยากสงสัยนะครับก็ใครที่มีคำถามนะครับสามารถยกมือถามได้นะครับ I believe many of you must have some interesting questions. We would like to open the floor for Q&A session with Dr. Fujimoto. If you have a question, please raise your hand. Okay, first question มาแล้วครับนี่ครับในนามของ Space TH นะครับสื่ออวกาศออนไลน์นะครับ
Okay, I have a question. So when the Hayabusa 2 is launched, so what gives your mission team to achieve the great success, right? Escapely compared to the challenge to face to the Hayabusa 1, what you just learning from the Hayabusa 1 and give you a trust your Hayabusa 2 is have the great successful of the mission?
Yeah, very good question. So for Hayabusa 1, it was, in this asteroid sample return mission, you get to the asteroid and circle around rendezvous with the satellite for a certain amount of time. And during that period, you perform some touchdown operations. For Hayabusa 1, we only had like 2 weeks. But for Hayabusa 2, we had 1.5 years. So, in the first mission, we thought everything will go as we had planned. So maybe 2 weeks will be enough. It was a really almost like amateur. But we managed to get some sample from Hayabusa 2, so it was a success. Hayabusa 2 was a success. Hayabusa 1 was a success, but at the same time, we learned lots of lessons, and we were honest enough to apply those lessons. So for Hayabusa 2, we realized that we should learn a lot after arrival to our target asteroid. By arriving more, you can arrange the hardware better. You can know how the spacecraft behaves better. So it was really like the lessons that we know nothing until we get there. After we get there, we accumulate our experience and start to drive your machine like a racing driver instead of an amateur driver. So that was the lessons learned. So it was like the Hayabusa 1 was a success, but we thought that we can do better. We knew that we can do better. And in order to do better, we were honest enough to realize that there aren't many you can prepare ahead of time. You have to learn a lot after you get to the target asteroid. I think that was the thing. And the reason that we made a success for the Hayabusa 2 is that we have brought this target marker. And I didn't go into details, but original plan was that we should be able to perform 3 touchdowns. The first 2 very easy, because we were thinking that there should be a big flat area on the surface, which were not there. But for the third touchdown, it can be, you have to succeed, but we can try a new technology. That was the original thinking. So that's the reason why we brought target marker with HABS-2. It was not for the normal landing. It was for this third special, for the fun operation, we brought the target marker. But then that target marker was critical to the real operation, even for the first touchdown. So we learned the lessons from the previous missions, but at the same time, we always wanted to add something more for the future missions. So it was a real nice combination of the two that made this HABS-2 mission very successful.
ครับมีคำถามเพิ่มเติมไหมครับสามารถสอบถามได้นะครับเชิญครับ
Okay, I have about 2 questions about the Hayabusa missions. Okay, the first one, you're talking about the protostar disk, and you're talking about the snow line, and I would like to know how do we know that line exists? Do we have any physical evidence? And is this different from the habitable zone?
Okay, good. That's a good question. Yes, so we know a protoplanetary disk. So and then we know what the star looks like. So you can do the thermal modeling. You know, there's a radiation coming from the central star, and here's the structure. So you can calculate what the temperature distribution will look like within the protosolar disk. And then with that calculation, you come to the number that's the snow line should exist around 2 AU from the star. So it's really the radiation coming from the star, central star, and the structure of the disk. And with that, you can calculate the temperature distribution. That's the thing. And then the second question was a habitable zone. Yeah, so snow line is like the temperature. You know, in the protoplanetary disk, the pressure is so low that it's either vapor or ice. There's no liquid water in space because the pressure is low. So when you say snow line, it's the demarcation line between the vapor and ice. But when you say habitable zone, it's a place where if you locate a planet with a dense atmosphere, and then you can calculate the surface temperature. And because you have enough pressure, if it's in a nice zone, then the water can exist in the form of liquid. So it's when we talk about snow line, it's really about, we're also almost talking about the vacuum environment. But when you talk about the habitable zone, it's about the surface condition of a planet. So you're assuming the atmosphere to be there, and you're thinking about the existence of liquid water. So the pressure condition is very different when you talk about these two things.
Okay, thank you. And one more question. Yeah. After we got a sample from the Ryugu asteroid, okay, what do we learn from it?
Yeah, so there are many things we learned, but one very interesting thing, well, my most favorite thing is that, we knew that Ryugu is a primordial asteroid. We call it C-type asteroid. And there are some meteorites that seems to be coming from C-type asteroid. So the rough guess was that Ryugu sample will look like one of those meteorites coming from C-type. We thought coming from C-type asteroid. But it turns out that Ryugu samples look is very similar to a rare type meteorites. Not one of those typical meteorite that seems to be coming from C-type asteroid, but something that really looks rare. And that makes you think, because how did we pick Ryugu as the target asteroid? Well, we knew Ryugu had to be one of those primordial asteroids, which you can tell from the spectroscopic observation from the ground. But there's another condition you need. It has to be within the reach. It has to be within the distance range that you can do the sample return mission. And we only had 3 of them, and we just randomly, not randomly, but we just picked Ryugu because it just met the condition. So if you think about how we picked Ryugu, there was nothing special, but we just picked it because it looks sample returnable. So then the chance, the odd is that Ryugu must be a typical primordial asteroid. But when we returned the samples turned out to be a very rare type of meteorites that seems to be coming from primordial asteroid. So what does it mean? It means that meteorite samples are very biased. We've been studying meteorite samples, but we have been studying a very biased samples. So typical meteorite, typical materials in the meteorite collection is not typical in space. Ryugu must be the typical primordial asteroid in space, but the samples that is retrieved as meteorite doesn't reflect it. So after all, what it means is that if you want to get the correct data, you have to do the sample return mission. And I really like this message.
Okay, thank you very much.
I also have two questions.
Yes.
My first one is this snow line the reason why gas giants form?
Sure, good question. Yes, yes. Well, gas giants have to be beyond the snow line because for it to be giant, it has to collect many materials. And if you add ice particle to like silicate particles, you can enhance the mass. Yes, you're right.
And my second question is, what kind of like propulsion system did you use on Hayabusa?
Propulsion system, it's ion propulsion to get to, for the interplanetary cruise, it was the ion engine. But if you're in the close proximity of the asteroid, it's a regular, like hydrogen, hydrogen. It's a hydrogen, like a gas, but toxic gas, by the way. But so it's a regular thing. So, but again, that's a good question because our launch capability is limited. So the launch mass has to be small. An ion engine is very fuel efficient. So for the long-term interplanetary cruise, we utilize the ion engine. But for the proximity operation, we utilize a regular thing so that we can precisely control the operation. Yeah.
Did you use a Hall effect thruster? Or
No, it's not the other one. It's not that one, but it's the Hall thruster is the recent one, but it was the more traditional one that we used.
Okay, thank you.
Yeah, thank you.
My question will be about the institute. I would like to know that how will you form the team in this institute, ISAF, and if under JAXA, so how will you cooperate with another institute or another division inside JAXA?
Yes, very good question. So when it comes to a mission like this, there has to be somebody who proposed the mission. So there's a very hardcore team centered around the proposers. That's mostly researchers. And then, but when it comes to the really operation, when it comes to building the spacecraft, conceptually it can be like a team of 10 people or something. But if you want to do a serious planning, if you want to build the mission, if you want to operate the mission, it's going to be like 150 people. So one order of magnitude more, but it's like 150 people. It looks big, but compared to NASA, it's tiny. I think that with NASA, it's going to be like 500 people. But then we ask the engineers from the industry. We ask from the engineers from the different division to join, and we do that through the negotiation, but at the same time, in order to have that kind of negotiation successful, we really have to show how attractive the mission is, what it means for the younger people to join this mission for their career. They join the mission and get the experience for the 5 years. What does it mean when they become a senior engineer within the space agency. So those thinking are always behind when you try to form the team. We try to get, for space science missions, we try to get the younger people because in space science missions, it makes them think deeper because, we're doing something new. And we charge bigger role, bigger responsibility than other missions because, again, it's new. And we, in a sense, rely on the talent of the younger people who can spend more time on the mission rather than, taking care of their kids. So, yeah, maybe it's not a systematic way, but I think it works as long as we can make a win-win relationship with the talented younger people and the will of the institute to make a successful mission. So it's that kind of trustworthy relationship. I trust you, so I expect you to do this, and at the same time, the younger people expect that we will evolve the program into a more and more attractive things to perform.
May I ask more about the physical budget?
Oh, the typical budget for our like Hayabusa 2, which is our how do I say? Which is our what's the word? Flagship mission. Our flagship mission at my institute is like typically it's like how much is it? 300 million US dollar, something like this. Yeah.
Do you get support from JAXA only or from other source for the budget?
No, it's only, you mean in terms of budget, you mean?
Yeah, no.
Oh, we always ask for money. So it's really like, there's no secured budget. We always, whenever you come up with an idea of a new mission, we go to the government and say, hey, it's a nice mission, you have to support us. That's what I do every day, by the way. So, yeah, it's always like, hey, we have something nice to do, so why don't you support it, Maybe next time when we come up with a new idea, we go to the government and telling them that, hey, Thailand wants to join, why we should do this? So it's really this kind of language I'm always thinking. So the technology development is one thing, inspiring people is another thing, and the tool as the diplomacy, for international diplomacy, could be another issue. So, yeah, combining all those things, I try to make our mission as attractive as possible so that we can get a smoother support from the government.
Thank you.
Okay, I have two questions.
Yeah.
First, in the Hayabusa technique to the, I think that the touchdown and horn architecture is so difficult in the microgravity, have so rich and many variables. But I think how do you test the horn and touchdown mission in the Earth? I think the test and preparing the horn is so very difficult in because how you test the technique of touchdown in the world.
Okay, good. So two issues. So I did talk about two landing missions. One is to landing on the asteroid under microgravity, and the other one is landing on the surface of the moon. And as far as that operation is concerned, microgravity is much easier because you can redo it. You try and you think something is wrong, you can just go up, back again. When it comes to lunar landing, once you decide to go to the surface, there's no way back. Once you decide, for 20 minutes, you just have to keep on praying that it's going to be successful. Otherwise, you can all you can do is just to stare at the screen and you do not do anything else. So algorithm-wise, microgravity is much easier. But you're correct to say that when it comes to hardware testing, how do you recreate the environment where the hardware is going to work? Yeah, that's a good question. So you cannot do the full-scale testing of the spacecraft, but when it comes to component, you can do the drop tower test. You can go to the drop tower and see if the sampling mechanism will work in that environment. So that's what we do. Drop tower testing is what we do of the component, but not the whole system. Yeah.
Second, I see the in the real mission you change the point for touchdown mission. How to difficult to discussion for accept the change the point. In the Hayabusa 2, you change the point for touchdown mission, right? How in the engineer discussion, how to confirm the new point can drop the touchdown mission?
So what kind of discussion we had to decide where to land? Is that what you said? Yeah, it's an interesting question because so where do I start from? Like, sometimes, well, Hayabusa is a science mission. There's a planetary scientist who wants to do this or do that. So they always raise the bar high. They always ask the engineers to, hey, can you go there and get the sample? Can you do this? And the engineers are like, engineers always want to do something safer. But at the same time, the way in my institute, the way scientists and engineers works is very productive because thanks to NASA, as I said at the beginning, engineers understands that if we just go for the safer options, we are nobody. Nobody cares. We have to go for the bold option, but not for the crazy ones, not for the extreme ones. So I think thanks to the pressure that we have to show that we are something, while NASA is something doing great with a much bigger mission. I think that pressure is really making our engineers and scientists get together and form a nice team to go for something valuable. So it's really the mindset issue. It's really, are you a good team or not? And if you have a good team, the mission will be successful. But if the teams are not really good, I think we have a trouble. Because in exploration, in solar system exploration like this, you can perform many rehearsals. There are so many unknowns and there are so many surprises, and surprises comes only after you arrive at the target body, like asteroid or maybe Phobos. So, in preparing a mission, we make sure that we are building a spacecraft that will work. We make sure that we have a nice operation plan that we can perform once we get there. But the third issue is that we should be prepared for surprises. And that third element, it has to be a nice team. Otherwise, it will never work.
How long to discussion? One day or
that's difficult to tell because we are always talking. And but the formal meeting happened like 5 times. And my director of my institute back then, he was always like, he was a very, I don't know, because maybe he was in a position to say this, but he was like, don't do this, don't do this. So the team was like in the mood of, hey, let make him say yes. And I think that continued for 5 times. And at the final minute, my previous director said, yes, let's go. And that's how it happened. Yeah.
Okay, thank you.
มีคำถามเพิ่มเติมนะครับ
So thank you for your interesting presentations. I'm from Department of Earth Science, Kasetsart University. So as planetary science student, and you mentioned about terrestrial vetterings. So I do wonders about, is it any evidence for space vetterings on the Hayabusa 2 samples?
Oh, yes, that's a very good question. Yes, so samples from the first touchdown and sample from the second touchdown, they look really okay, except for one feature. It's the exposure time to the galactic cosmic ray. So if you are if you are from subsurface, you're not exposed to cosmic ray, but if you're on the surface, you are.
Yeah.
But other than that, there's no big difference. So space weathering there's no space weathering effect, I would say. So exposure, there's a difference between the exposure time, the cosmic ray, but that's it, and nothing really more. I'll put it that way, yeah.
Yeah, and for the second questions, Itokawa is the siliceous asteroid, while Ryukyu is carbonaceous asteroid. So I wonder if JAXA have any plan to study another type of asteroid.
Yeah, the obvious answer is comet, of course.
Yeah.
Which is not easy though, and yeah. So the comet, yeah, sample. I think we should keep on doing the comet sample return mission, but at the same time, if we keep on doing the same thing on and on and on, people will not support us. So I think if we have to go to comet, we are in the phase of developing a new technology. We shouldn't be performing Hayabusa 3. I would put it that way. We should be performing, even if we have to perform a small body sample return mission, it should be done in a more smarter way, more innovative way. And in that sense, and in order to develop that technology, you need a big support from the government. You need big money, and you need support from the government. So my strategy now is, let's talk about landing on Mars. Then through Mars landing program, we get support from technology development. And subsequent to Mars landing, we can talk about sample return from comet. That's my strategy. So yeah, obvious next step is comet sample return, but that's not easy. So let's take some time, develop the technology through Mars landing program, and then go to comet. That's what I'm thinking now.
Thank you.
All right, so you've mentioned in the last part that you are planning to land on the Mars, right? So I believe that the Mars surface is rather much more hostile than the Moon's. So other than the soft shell inflatable, that one is inflatable shell. Do you have anything else to improve the, let's say, probability of being able to be on Mars for longer time? Since I have heard that there is a lot of like storm on Mars.
So I think our strategy is that don't go for longer mission.
Okay.
Do your, I mean, it's a small mission, just do the focused work, but land on the right spot where you can do the job. Get there, do your job quickly, and forget about worrying about sandstorm or whatsoever, or surviving a long time on the surface. Do your job quickly, but prepare well enough so that once you get there, you can do your job. That's the strategy. So in that sense, we have to have the pinpoint landing technology for this aeroshell as well. The pinpoint landing technology on the Moon was done in a different way. For this, we use there will be a aerodynamics because of the atmosphere, and even in the presence of the atmospheric effect, we should be able to perform a pinpoint landing with this kind of hardware. I think our improvement will be in that direction. Do the pinpoint landing, get there, do the job quickly, and think about the next mission. That's my strategy. Yeah.
Okay. All right. Thank you.
มีท่านใดมีคำถามเพิ่มเติมไหมครับตอนนี้เรามีโอกาสดีที่ถามวิทยากรนะครับไม่งั้นเราต้องบินตามไปที่ญี่ปุ่นนะครับไปคุยที่ญี่ปุ่นต่อนะครับ
So in Thailand, people ask 2 questions. That seems to be the fashion here. I'm learning.
โอเคครับครับในช่วงสุดท้ายนี้นะครับจะขอเรียนเชิญนะครับดร.นำชัยชีววิวัฒน์นะครับหัวหน้าโครงการความร่วมมือระหว่างสวทช.กับ JAXA นะครับมากล่าวปิดการบรรยายในวันนี้นะครับ And now to conclude our lecture, I would like to invite Dr. Namchai, head of the collaboration project between NASDA and JAXA, to deliver the closing remarks for today's event.
Thank you very much, Dr. Fujimoto, for your very exciting and entertaining talk. For myself, I think you give us many things, but briefly, first, I think that you not only talk about the space exploration, but you're talking about ambition, the ambition of humankind. We as humankind, we want to learn, we want to know, we want to answer many things. And second, we always have problems, and we need to develop a power to solve the problems. This is very important for our futures. And the last thing I learned from your talk is we need to find our niche for any work or any question. For example, as you say, focus, quick and small, but smart for in your case. I think we need to do the same thing for our space projects for Thailand also. And your talk is very nice. It reminds me when I'm translating book of my hero, the astronomer Carl Sagan. So he wrote a book called Pale Blue Dot. It's about the space exploration. In Thai language, it will be published in a few months. In the next few months, and I'm the translator. I'm glad and I'm happy and feel the same when translated that book and when listen to your talk. Thank you. Let's give our big applause for him. Yeah, thank you, Doctor.
Okay, on behalf of the organizers, I would like to express our sincere gratitude to our distinguished speaker, Dr. Fujimoto, for the insightful and inspiring lecture. Thank you everyone for your participation today. We hope you have a wonderful evening. หวังว่าพบกันใหม่ในโอกาสหน้านะครับ ขอบคุณมากครับ สวัสดีครับ